All right, you guys, it's the last one. I want to say thank you again very much for your dedication, for your stick-to-itiveness as it relates to these problems. I know there's a lot of physics here, and I really do appreciate all of your effort. This last question actually is an example from your textbook. It's example 10.5, so it's actually from chapter 10 because they put all of the kinetic energy stuff together in the textbook the way that the authors decided to write it. So let's take a look at this question real quick. This is just some computational work with the same material that we've been doing. So we've got two bikes. Bike one has a 10-kilogram frame and 1 kilogram wheels. Bike two has a 9-kilogram frame and 1.5 kilogram wheels. So they both have the same total mass. That's all well and good. The question is, what is the kinetic energy of each bike when they're ridden at 12 meters per second? So if I had asked you this 3 days ago, you would have said, oh, they're the same because they've got the same mass, they've got the same velocity, 1/2 mv squared, bam, bam, we're done. But now we've realized, oh, this rotation stuff matters a little bit. So that's where we're going to jump in. I'm going to do these two bikes, kind of take a look at them separately, and then we'll do some calculations. So bike one has the mass of the frame is 10 kilograms, and the mass of the wheel is 1 kilogram each. So that's a total of 2, but we'll just remember that there are 2 of them. And bike 2, the mass of the frame is 9 kilograms, and the mass of the wheels is 1.5 kilograms each. Again, we're going to remind ourselves that there are 2. So in either of these cases, we just need to figure out how to calculate the total kinetic energy. So we know that there is translational kinetic energy, and we're reminded that there is also rotational kinetic energy. The translational is that same old 1/2 mv squared that we know and love. And when we're talking about translational, not only is the frame moving, but the wheels are moving as well. So when we calculate that one out, this is going to be 1/2 the mass of the frame plus 2 times the mass of the wheel times that translational velocity, okay, squared, just to be very clear. And I should write in here that both of these bikes have a velocity, a translational velocity of 12 meters per second. Okay. Now we also have this rotational stuff. So I'm going to do that over just so we can kind of note what it is. We know that there are actually going to be 2 of them, right? Because we've got 2 wheels. And each of those wheels, when they're turning, we've got 1/2. So it's going to be that disc. We can go ahead and look it up one more time just to verify. But when we take a look at the thin-walled hollow cylinder, that is what a bike tire is. It's just mr squared. So here we go. We're going to go ahead and write that as mr squared in our equation. And then we've got omega squared. Doesn't say anything in here about omega, but thankfully for us, we remember that V is equal to omega R, or in this case, if we're going to go ahead and solve for omega, omega is equal to V over R. So instead of writing omega, I'm just going to write V over R. Life is a little bit easier. So it's going to be 1/2 mr squared times V over R. Remember, that's all squared, which means that this R squared and this R squared are going to go away. So when we start to add these values together, we can see that the total kinetic energy is going to be 1/2 of the total mass, so the mass of the frame, plus 2 times the mass of a wheel times the velocity squared, okay? Plus 1/2, I'm going to write this a little more nicely, sorry, twice of 1/2, because it's 2 wheels, right? Times 1/2 the mass of a wheel times the velocity, that's the translational velocity, squared, okay? And then we can just kind of plug things in for each of our situations to see what we get. So for bike number 1, we've got 1/2, so that's going to be 10 plus 2, which is 12, right, times 12 squared plus, well, the 2 and the 1/2 are going to cancel, aren't they? So that's just going to be the mass of a wheel, so that's going to be 1 times 12 squared. And when I worked that out, so that's going to be 6 plus 1 is 7 times 144. That gave me, if you're following along in your textbook, they round that up to 1010 because of sig figs. For bike number 2, similar process, different numbers. We've got 1/2. So now we've got the same 12, we've got the same mass times 12 squared. So that part all is the same, but this is where it's different, right? We've got the mass of each wheel is 1.5 times 12 squared. And you can see pretty easily here. So that's going to be 6 plus 1.5, or 7.5, gives me a total kinetic energy for that second bike of 1080 joules. Okay, so we've got a different value because the distribution of that mass is different. Same mass, different distribution, more rotation, and thus more kinetic energy. You can think about that in terms of the work energy theorem. Think about that in terms of how much work you have to do to get that bike, that second bike moving. We have to put a lot more energy into this bike to get it to be moving at the same translational speed as you would for the first bike. Thank you guys again. Have a great, great day.